All right, welcome to another session of DGX Compare. Today we're working on DiffusionGemma 26B. And this is a pretty special model because it's a derivative of one of my favorite models, Gemma 26, Gemma 426. And what makes this model special is that it's actually working with what's called diffusion. And diffusion is the way that Google or the Gemma team sets up block diffusion decoding. And essentially, we've been doing a lot of speculative decode testing of late with other models, but block diffusion decoding, what it does is rather than guess every next word from left to right, what they do is they create this index of a full 256 token canvas at the same time. And what it does is it replaces text with random vocabulary noise, and then it gradually refines the whole block over multiple parallel denoising steps, right? So what essentially it's doing is when you're typing words in, it kind of knows ahead of time what the words are going to, what you're trying to gain and gather and execute. And this makes the tokens per second during decode much faster, right? And it's not just one way. It also allows for back and forth. So it's bidirectional essentially. So anyways, so yeah, this model we have installed on two devices today. The one to the top is on the DGX Spark there. It's actually clustered right now, but we're actually using single node. This is a pretty reasonable model to be fit into one device, and on one device it's barely taking up any space. It's 83% of memory usage, so it's pretty stable. And on this bottom screen, we're actually loading it from this MacBook Pro with 48 gigs of VRAM. They're both running bare metal, or in terms of Mac metal. So no containers. It's pretty much running as close to the CPU or GPU as possible. In this case, both of them are running unified memory, so it shouldn't be too bad, and things should relatively be fast. So our typical question, there you go. We'll have to pre-type this in, so I'll have to do it now. Ugh, I'll type it. Tell me all about Tyranna. I misspelled Tyrannosaurus on purpose. And we'll do the same for DGX. Tell me all about Tyrannosaurus Rex, misspelled. And let's give it a spin. Now, oh, by the way, this is quantized 4-bit on the NVFE4 on the DGX Spark, and it's 5-bit on the Mac, because we tried to get 4-bit working. It's just there are a lot of issues with 4-bit, but 5-bit seemed pretty stable, so we're sticking with that. So we'll click on the Mac first, and then we'll click on the Spark second. And as you can see, Spark's prefill, wow, it's fast, but it looks like Mac is just as fast. So I think the Spark started earlier, and they both had really fast decode because it's a smaller model, but the Mac was pretty good too. This is the feathers one, so let's click on feathers there, and feathers on the top. So again, see that Explorer came up first, and then this block showed up on the Mac, and then that completed, and this completed, and there's the follow-up. We're still waiting for the follow-up there. Okay, there's the follow-up now. How did T-Rex hunt a Triceratops? Is there a Triceratops one here? Let's do that. So I don't traditionally work on smaller models like this in terms of tokens for speed, because it's all really, really fast, and everything pretty much fits on the DGX. What I wanted to test here was, again, the diffusion technology. And so far, so good, pretty impressive. Now the question is whether or not the data is correct, right? And a lot of the Tyrannosaurus stuff is pretty subjective. I mean, I don't expect to see the same result every single time. Different models give different kinds of results. If you want to be empirical or definitive, or I guess deterministic about it, we should really be looking at files and code. So let's go ahead and do that. So let's open up a new chat. And let's try our trusty Airbnb file today. 100 rows of Airbnb. And then let's do the same thing on the top. 100 rows of Airbnb. And let's not forget to turn on the code interpreter for both. And then let us have a notes document that actually has the exact query to use or prompt to use. I'll do the same for the top here. That's weird. Let's grab it from here. Okay, so we have the prompts in place. This is, well, we'll run it and then we'll talk about the file. So this file here, we've already done ahead of time. This is Gemini, and so 99 rows, 79 columns, 161 and 109. So let's see. Well, that's working. Oh, there we go. The Spark is already done. Let's see. 99, 79, 161, 109. Good. 99, 79, 161, 109. Great. That's pretty fast. Let's do additional stuff. What's the average price for each room type? And are there any correlation price and other variables? Actually, that's actually not fair. This is a lot easier in terms of the query, because that one right there is doing a lot of correlation testing. Let's do missing variables. Actually, no, histogram. Can you create a histogram to show the distribution of prices? And here, same thing, histogram. Now the answer is they're not gonna be able to make a histogram because they don't have the technology, right, or the plugins for that. But let's see what it does. So this one says I don't have access to the full data set. That's a problem, right? You actually do have access to the full data set. It's just that you're running out of memory. Here, it's actually trying to execute the code. And what I expect it to tell me is that I can't draw a histogram. However, here's the code that would do so. Oh, yeah, see? And so I think that's a kind of one of the reasons why we try to use different RAM levels. Now, both of these fit in the VRAM that we've allocated to it, but the main difference is the extras, right? So the KV cache, obviously, on 128 gigs of VRAM or unified combined VRAM is a lot more than the 48 here, right? So right now we're close. We're 36 out of 48, whereas here we're 108 out of 130. So there's still 20 left, and whereas here you only have like 12 left, right? So it's a KV cache. Now let's do the big test. The big test is when you actually start using bigger files. So let us actually install this 1K rows. This is 2.8 megabytes. Let's do that one by one here. So I'll pick up this file. It's 2 megabytes big. It's 1,000 rows. And then it'll take a couple of minutes to add that. On the top, I'll do the same. Files. 1K rows. So just be clear. This IP is 65 and this IP is 58. So let's let it load for a few seconds. I think this should be about a minute. And while that is going, let's have the awesome view of the CPU. I think people like to see this happening. There's not much going on other than trying to load the files. On this end, you just kind of it's really fun to see which cores actually are being used. We've seen it before where 16 and 17 are like 100% and everything's kind of sporadic around. But for this, the 20 cores, the 20 CPUs are pretty even across the board at 20-something%. On the Mac side, really not that interesting. It's just, you know, a straight green line. But as long as we are green and not yellow, we are good. Okay, so Mac is finished loading. Let's put our trusty little query there. And using the attached CSV file, write and execute Python code. Using pandas, load the file directly. And compute the mean, median, max. And then report the top 3 most common root type values. And then show me the actual executed output, and not just the code. That's the same thing. Let's wait for it to finish loading. I don't exactly know why, but whenever we do this, the Mac seems to load up a lot faster when it comes to data load or data ingestion into RAG, or at least session RAG. I gotta research that more, why it is that Mac is always faster all the time. So, interesting. That's actually kind of lowered. I wonder why that is. It was 20-something% across the board earlier, and now it's like 13%. Anyway, that's still loading. You know what I'm going to do? I'm going to actually... No. We should watch this both at the same time, so everybody can see what the prefill looks like and what decode looks like. So just bear with me. In the meantime, I will continue tracking. Which things are running here? Gosh, that's really slow for 2.4 megabyte file. That was not a good experience at all. For those who, since that's still loading up, for those actually who don't quite know OpenWeb UI, there's a functionality where you can actually ingest this ahead of time. And the way you do it is to actually go to I think it's admin panel, settings, and then models. And then, well, actually, let's make sure first that the thing's coded in. So DiffusionGemma, let's make sure code interpreter is in there. Okay, that's proper. And then what we'll do is we'll actually go to settings, workspace, and then models. And what you do here is you get to create, pick up a model, and then what you do is you can actually ingest the information. Let's see if we can create that really fast. Really fast there. And then what you do is you open this up right here, and then here for knowledge upload, see that? You can actually have a collection of files you can add in and enable, and the Airbnb files would be included in there. But, anyways, yeah, we'll do that for another assignment. Let's take a look. Is it actually loaded up yet? Oh, okay. Good, good, good. So they're both loaded up. All right, let's do the token speed comparison. I'll start with the Mac. Click. And then click. They both say retrieve one source. Oh no, I just realized I did not enable chat level code interpretation. That's not great, but you know, usually many of the models have failover and they'll tell you they can't calculate it. So we have a chance to do it again. Okay, so here it says, I'm sorry, I don't have the capacity to execute Python code directly, and it stopped. And here, that's interesting. This one actually tried to calculate it, and look at that. It's giving us incorrect information. It's telling us there are 3 rows and 19 columns. But we all know there's actually 99 columns, sorry, 79 columns, and this is a 1,000 rows, so it should be telling us 1,000 rows and 79 columns. So it's actually told us incorrect data. But over here, it's at least telling us I can't do it. Let's do that again. This time I will turn on the code interpreter. I will paste the same text from earlier. Oh gosh, where did text go? Actually, you know what? Let me grab the previous. And over here, I'll do the same thing. I'll enable code interpreter, paste the same text in, and then do the run. Do the run. So now it's executing the code. And again, telling us incorrect information. And then over here, it's still going. And this time around is actually shown as what looks like correct information. 999, 79 columns, that looks about right. I'm gonna go into Gemini over here. And then have it analyze exactly the file. And the expected results are that was so fast. 999, 79, 211, 131. 9979, 211, 131. So they're actually correct. But the scary part is what's going on here on the Mac, right? It has just given us the incorrect information. The price statistics mean of 556. And the mean is actually 211. And let's see, has it said anything about it not being able to handle it? No, right? That is not a good thing, because essentially, if I completely forgot that I had to click on that, and I just didn't notice because I'm really busy, I would not have noticed that these numbers are incorrect. And it looks like all of this is hallucinated or just frankly made up. So that's not a good thing. Now I'm trying to figure out, I'll be figuring out whether or not it's Mac specific or MLX specific. But it seemed okay over here when it comes to tooling. Now, remember earlier we actually didn't have the problem when we were working with a smaller file? Well, I think that's because memory was still good, right? We haven't bumped into any kind of memory issues. So anyways, I think you guys should have figured out by now why we didn't run this test on the the Mac Studio. And it's to demonstrate what happens when you have a model that fits into memory, but then KV cache gets close to max, but you're never really told that that's the case. And then all of a sudden, it starts to spit wrong data from RAG. If we were to rerun this, in fact, we actually already did, but if we reran this on the Mac Studio with 96 and Ultra 3, it's fine. It shows this, what we saw there. But when you're getting dangerously close to the maximum amount of memory that you have, things like this happen. So moral lesson, something can be fast, something can be blazing, but it doesn't necessarily mean that it's accurate. So be careful when you guys are looking at your results, and don't always trust that a model will be correct with larger data sets because you verified it with a smaller data set. Memory is king, or memory is the most important factor, so be careful with that. We're going to be doing several other videos where we do this when we're comparing graphics cards. We have a 16 gigabyte and 32 and 24 gigabyte graphics cards for the PC, and we've noticed this happening quite often because large language models barely even fit in them, and things like this happen. And there are some good models that have a good error handling and fail-safing to tell you, hey, like, I can't do this, or I'm hallucinating. I think Laguna did a really good job doing that, and I think Quen did a really good job doing that. But I'm surprised that this model does not. All right, that's it for today's session. This is DiffusionGemma 26B, quantized 4-bit and quantized 5-bit on a MacBook Pro and a DGX Spark. See you guys next time.